Part 1. The mystery beneath our feet. 65 million years before the first city rose, strange metallic spheres were already falling across the Earth. They scatter through ancient rock like the debris of a nuclear test, but humans didn't exist then. So who or what left this signature behind? Beneath ancient layers of stone, scientists have uncovered something that should not exist. Microscopic metal spheres scattered across rocks tens of millions of years old. They are not arranged randomly. Instead, they follow a strange, repeating pattern, one eerily familiar to those who have studied the aftermath of modern nuclear detonations. These tiny spheres appear embedded within distinct layers, only fractions of a millimeter across. To the naked eye, they might look like dust, but under a microscope, they reveal something different. A metallic sheen, surfaces smoothed as though melted and reformed, and chemical structures that resist easy categorization. The most unsettling part is not their appearance but their distribution. They appear globally synchronized, showing up in strata from continents separated by wide oceans, as if scattered by some force that encircled the planet itself. The rocks in which they are found are often more than 60 million years old, deposited long before the emergence of humans, before agriculture, before even the first primates began their climb into higher intelligence. Industrial society did not exist then, yet something left behind material traces that mimic, almost exactly, the fallout we see in the modern era when great powers tested nuclear weapons. What makes them unusual is their chemical makeup. The surfaces contain exotic blends of metals in proportions that are difficult to match to volcanic activity. Certain ratios of nickel, chromium, and even rare earth elements do not follow known natural pathways of formation. The mixes appear as if they were engineered alloys rather than chance results of melted minerals. Part 2. The iridium boundary. A thin, grey layer of clay runs like a scar through rocks around the world. It is only centimetres thick, yet it marks one of the darkest chapters in Earth's story, the sudden end of the dinosaurs. What makes this layer extraordinary is its unnaturally high content of iridium, an element that is rare on Earth but common in asteroids. The discovery came in 1980 when scientists measured chemical traces within this thin boundary. Buried between the chalk layers of the Cretaceous and the overlying deposits of the Paleogene, the clay they analyzed was loaded with iridium far beyond what geology could easily explain. To the scientific eye, this was no accident. It hinted at something extraordinary settling out of the sky before being locked in stone. What ultimately tipped the balance was evidence found far beyond that clay seam. Around the world, scientists uncovered shocked quartz, microspherules, and even a vast crater beneath the Yucatan Peninsula. Together, these strands told a coherent story. A colossal asteroid struck Earth, spreading molten debris, injecting dust into the atmosphere, blocking sunlight and collapsing ecosystems almost overnight. The lesson here is stark. A catastrophic event that lasted only hours left traces visible 66 million years later. The asteroid was reduced to fragments almost instantly, but its chemical calling card imprinted itself upon the entire planet. It is proof that the Earth's rocks are not just dead matter, but an archive, faithfully recording moments of transformation and destruction across unimaginable stretches of time. If an asteroid impact can announce itself so loudly across the geological record, it forces us to consider a larger question. What might an entire planetary civilization leave behind? A single rock from space scattered its elements worldwide. The combustion of entire industries, the refining of metals, or even nuclear exchanges conducted over centuries would leave traces of their own, maybe not in the form of towering structures we could hold, but in isotopic ratios, chemical residues, or unexplained concentrations of elements. Part 3. The Silurian Hypothesis. What if we weren't the first industrial civilization on Earth? The very idea sounds like science fiction, yet it has been seriously raised by scientists who wondered whether we could detect signs of a civilization that predates humanity by tens of millions of years. They gave the idea a name, the Silurian Hypothesis. The scale of the question is staggering. Our industrial era is barely 10,000 years old. That seems expansive when compared to recorded history, but against the age of the Earth it is little more than a single spark in a great dark sea of time. Our 4.5 billion-year-old planet has cycled through ice ages, scorching hothouse climates, shifting continents, and countless ecosystems. If you compare that timeline to a calendar year, human civilization accounts for less than a single day. Even more humbling, the industrial age fits inside a few brief minutes on that calendar. Now imagine looking backward not just 10,000 years, but 10 million, 100 million, even a billion. That immensity dwarfs all of recorded history. The surface of the Earth is not a fixed archive. It is constantly recycling itself through erosion, tectonic activity, and volcanic resurfacing. Oceans open and close, mountains rise and vanish, entire regions are subducted back into the mantle. Evidence that seems solid and permanent to us may be erased on scales of only a few million years. Consider archaeological sites from our own recent past. Without active preservation, buildings collapse, monuments weather, and metals corrode in under a century. What would be left after millions of years when glaciers advance and retreat, when rivers scour valleys, and when continents collide? Even the deepest stone records show gaps where sediments never formed or were later destroyed. The Earth is an editor that constantly rewrites its own archive, erasing entire chapters without hesitation. This is the tension behind the Silurian Hypothesis. If an industrial civilization existed long before us, the ordinary artifacts we associate with technology would almost certainly be gone. The question is whether subtler signs might be preserved. We may never see fossils of skyscrapers pressed into ancient rock, but we might detect shifts in isotopes, unusual concentrations of chemicals, or leftovers of industrial reactions locked within sediments. Part 4. Techno-signatures in stone buildings collapse. Metal corrodes. Monuments crumble into dust. In the short span of centuries, almost everything we think of as permanent begins to fade. Over millions of years, entire landscapes erase themselves and recycle into new forms. So what kind of evidence truly lasts long enough to point to an industrial civilization that lived in the distant past? The answer scientists suggest comes not from visible ruins at all, but from what they call techno-signatures, chemical and physical markers that outlive the cultures that produced them. These fall into several broad categories. The first involves residues from energy use. Every civilization that gains control of fire, fuel, or high-temperature processes inevitably alters the elemental mix around it. Combustion releases certain isotopes into the air and water. Over time, those isotopes enter sediments and become locked away. The second category involves atmospheric changes. Large-scale use of stored carbon can shift ratios of gases and leave a measurable mark long after the air itself has been exchanged. The third involves persistent waste. Synthetic byproducts, unnatural alloys, and complex polymers may resist natural breakdown under certain conditions, persisting for spans far beyond the reach of ordinary artifacts. One candidate for a durable trace lies in isotope ratios. The carbon cycle contains both light and heavy forms of carbon, and their relative proportions in rock layers can tell us how much carbon entered the atmosphere in the past. Large volcanic eruptions create distinctive spikes. The burning of massive stores of fossil fuels like coal and oil would create its own pattern. Human industry already shows up this way, with a sharp decline of the heavier isotope in recent layers. If something similar occurred millions of years ago, we would not need ruins to confirm it. The rocks themselves would carry the memory in altered ratios. Beyond isotopes, synthetic molecules raise another possibility. Some compounds produced only through modern chemical processes are astonishingly stable. Under the right conditions, they can resist heat, pressure, and microbial breakdown. In modern times, these range from long-lived pesticides to complex industrial polymers. If an ancient civilization manufactured equivalents, their presence might still be detectable in sediments today, even at levels invisible to the eye. Part 5. Nuclear shadows. 2 billion years ago, deep in the crust of what is now Gabon, Africa, the Earth did something that seems almost impossible. It built its own nuclear reactor, not a machine designed by intelligence, but a series of uranium-rich rock deposits arranged by chance in such a way that sustained fission reactions took place for hundreds of thousands of years. This phenomenon, called the oclo-fossil reactors, left a clear message in stone. When atoms split and release energy, the isotopic patterns in surrounding material change forever. Even though the reactors went cold long before humans existed, we can still see their fingerprints today. The oclo reactors work because natural uranium contains mostly uranium-238, with only a small fraction being uranium-235, the variety capable of sustaining a chain reaction. 2 billion years ago, uranium-235 was more abundant. Add water percolating through the rocks, acting as a natural moderator, and the conditions aligned to create a self-sustaining nuclear process. This natural experiment proves something vitally important. Nuclear energy leaves a durable, unmistakable signal in the geological record. Surrounding minerals show altered ratios of isotopes, evidence of elements consumed and created through fission. Certain isotopes of neodymium, ruthenium, and even xenon do not match natural distributions because some isotopes are preferentially burned up or produced in a reactor environment. These alterations are still measurable today, 2 billion years later, and this is where the mystery deepens. Because if natural reactors can survive in the geologic record for billions of years, so too could artificial ones. When scientists encounter other isotopic anomalies in ancient rocks, anomalies that echo the same profiles we see in controlled fission reactions, the comparisons begin to sound troublingly familiar. For example, there have been reports of rock strata containing traces of plutonium-244, an isotope with a half-life so short it should not still exist naturally, except in infinitesimal remnants from the birth of the solar system. Its discovery in certain contexts raises questions. Was it delivered only by cosmic processes, or could it have been artificially generated? Similarly, unusual distributions of uranium or thorium isotopes sometimes look less like natural decay and more like the byproducts of deliberate reactions. Nuclear reactions have unique permanence. Plastics can decay. Carbon isotope shifts can be confused with volcanic emissions, but nuclear residues stand apart. Their isotopic distortions cannot be replicated by ordinary geology. To create certain isotopes, high-energy processes are required, processes that mimic what human reactors and weapons unleash. Part 6. The Cycle of Forgotten Civilizations. Species rise, dominate the planet, and then vanish. From trilobites that once filled the seas to dinosaurs that ruled the land, life has always followed a cycle of emergence, growth, and disappearance. But what if intelligence itself is no different? What if it too is subject to the same rise and fall, repeating across vast eras? Our story may not be the singular arc we imagine, but one chapter in a much older sequence of cycles. The Silurian Hypothesis expands this line of thinking by asking not only whether one civilization might have existed before us, but whether multiple waves of intelligence could have risen, each separated by millions or even hundreds of millions of years. Picture the Earth as a stage upon which intelligence appears intermittently. Civilizations may flourish, transform their environment, collapse and vanish, only for the planet's surface to reset. Each leaves behind traces, but those traces are faint, scattered in sediments, obscured by tectonics and overprinted by new life. What survives are not ruins and monuments, but anomalies in chemistry, isotopes and mineral patterns. Life has been abundant on Earth for more than 500 million years. In that span, there have been 5 mass extinction events, each dramatically reordering ecosystems. Between these events are vast stretches where ecosystems flourished for tens of millions of years before being pruned. Each one of those stretches presented opportunities. The Permian lasted nearly 60 million years. The Cretaceous lasted around 80. Measured against our 10,000 years of industrial society, those spans are almost unimaginably broad. This perspective reframes how we think about lostness itself. Archaeology is full of forgotten places reclaimed by forest or desert, only to be rediscovered by chance. Extend that from the scale of thousands of years to millions and the equations change drastically. Cities vanish, continents drift, basins fill, rock cycles recycle everything. At that depth, civilizations themselves become lost cities of the planet, hidden not beneath sand but beneath time, which leads to an unavoidable implication. Humanity may not be the first to awaken Earth. Our existence could be the latest chapter in a repeating cycle of rise and collapse. Each previous wave may have consumed resources, altered the atmosphere, or changed ecosystems, leaving only fragments to hint at their passing. Then silence would return until evolution opened the possibility again. Part 7. What would we leave behind? If humanity vanished today, swept from existence in an instant, what story would the Earth tell in 100 million years? Would future geologists sift through our ruins and reconstruct our cities, our machines, our histories? Or would nearly everything we've built collapse into silence, leaving only the faintest traces? The unsettling truth is that in the deep time geology works with, most of the things we consider permanent would disintegrate. Skyscrapers, roads, even monuments of stone would be erased by shifting continents, relentless erosion, and the recycling engines of plate tectonics. What endures more than iron or glass are the subtle markers buried in chemistry. Consider what happens to the visible structures of civilization. Steel corrodes in decades. Concrete fractures and crumbles in thousands of years. Even the largest artificial monuments cannot resist glaciers, earthquakes, or volcanic flows forever. Cities that today span hundreds of square miles would, over millions of years, be compressed into rubble, then sediments, and eventually subducted into the mantle beneath turning tectonic plates. From the perspective of geological time, urban landscapes vanish almost instantly. So what then would remain to tell the story of humanity? If not the monuments and objects, then it must be the shadows of our activities on Earth's chemistry. One obvious fingerprint is the carbon record. The unprecedented burning of fossil fuels has already shifted the balance of carbon isotopes, pushing ratios sharply downward. It is a signal impossible to erase because it is captured inside sediments, shells, and soils worldwide. Millions of years from now, that ratio will still reveal that enormous stores of buried carbon were combusted in a geological instant. Alongside that signal come radionuclides, unstable isotopes created in reactors and through nuclear weapons testing. Unlike anything natural, they spread in the 20th century across every continent. Cesium-137, iodine-129, and others sank into oceans, soils, and ice. They have half-lives ranging from decades to millions of years. Even after many decay steps, their daughter products still betray their origin. In deep time, these isotopic anomalies would form thin bands detectable in rock cores. Here would lie humanity's unmistakable marker, the sign of a species that split the atom. Synthetic compounds add yet another layer. Modern chemistry has produced thousands of molecules unknown to nature. Some degrade quickly, but others linger. Long-lived fluorinated gases do not exist outside human activity. Compressed into sediments, they could survive well beyond human extinction, waiting to be identified millions of years later. If discovered in ancient strata, their presence would stand as undeniable evidence of technological action. Together, these chemical shadows form a pattern. Carbon isotopes plunging in ways natural cycles cannot explain, plastics cemented into rocks, nuclear residues forming thin bands across sediments, synthetic molecules frozen where no natural system can account for them. Part 8. Reading the rocks. The question is not only whether an ancient civilization once lived and fell, but whether our own age will someday be misread as natural history. Future geologists may examine a thin seam of carbon, isotopes, and plastics, wondering what force shaped it. To avoid that fate, we must look at Earth's deepest layers through new eyes, learning to read whispers hidden in stone, sea, and sky. Time strips away almost everything, yet it never forgets chemistry, and perhaps within those faint chemical scars, the voices of civilization still surround us, silent, patient, and waiting to be recognized. Air bubbles locked inside ancient ice can trap the atmosphere exactly as it was, carrying a record across hundreds of thousands of years. When scientists drill deep into ice sheets and extract cores, what they uncover isn't only frozen water, it's the preserved air of vanished worlds. Tiny capsules of atmosphere, perfectly sealed, sit embedded like fossils in the ice. What makes these icebound records remarkable is their precision. A layer of snow falls, compacts, and eventually becomes glacial ice. The spaces between crystals get sealed off. In each bubble lies a sample of the planet's sky from the year that snow settled. Stack enough layers and you build an archive stretching backward, thousands upon thousands of entries preserved in sequence. One of the most striking lessons comes from abrupt carbon dioxide changes. In several instances, the ice reveals rapid surges of CO2 that arrive on scales too short to attribute easily to volcanic activity. Alongside these surges, nitrogen isotopes shift in ways that imply sudden alterations in the chemistry of the atmosphere itself. Natural systems usually change slowly and predictably. Here the record shows pulses that look more like massive releases, sudden injections of gases mixed in ways that hint not at gradual adjustment but at intervention. This is why the atmosphere looms as one of the strongest possible carriers of techno-signatures. Unlike artifacts buried in soil, unlike metals corroded in ruins, the air records changes immediately. When an industrial civilization burns fuel, the gases spread within years and settle into every part of the globe. When synthetic compounds are released, they leave chemical ghosts that drift through the skies for centuries or longer. Some atmospheric compounds go further. Fluorinated gases, highly stable and entirely synthetic, resist degradation for spans longer than most natural cycles. If sealed in ice, their presence could persist far beyond their life in the open air. Imagine scientists cutting into strata millions of years from now and detecting molecules they know could never originate from volcanoes or combustion. Molecules that only deliberate chemistry can explain. If we treat the planet not as a static stage but as an active recorder, we must wonder what other layers may hold unsuspected revelations. Perhaps other anomalies already noted but dismissed as natural curiosities may yet hold deeper significance. And here we end our journey and continue in our dreams.